Hello everyone, I am Subham Kuswaha and today I will explain an exciting study on how to twisted tape insert and nanofluid can significantly improve the heat transfer performance in a tube. Did you know that the improving the heat transfer can save the massive amount of energy in the industry like power plant and the refrigeration? But traditionally heat exchanger are not efficiently enough that to where twisted tape and the nanofluid come in. In the normal heat exchanger, fluid flow in a straight line cause poor mixing and the slow heat transfer. Twisted tape create a swirling motion to improve the fluid mixing, while the nanofluid like the copper oxide and water enhance the thermal conductivity. But how do they together to work, and what is that study we are explore here, and this video is present my class project inspired by the international communication in heat and mass transfer research paper and demonstrated at a numerical channel flow simulation using the finite. So here is a table in this research paper. I am covering this the 5 step abstract governing equation and the numerical method, geometry boundary condition, numerical procedure, guide detail and validation, result and discussion and conclusion. So this is the abstract. This abstract, this study simulate the flow heat transfer of the copper oxide water nanofluid at the different solid concentration 1 to 4% in the tube under the turbulent condition where the Reynolds number is 3000 to 36,000 using a single phase model. The two phase model more accurate reflect real behavior results so that tube with the one twisted tip efficiency coefficient is a 2.18, where is the outperformance one with a two twisted tip efficiency coefficient is 2.04, making the twisted tape configuration more thermally efficient. And here the introduction part. Introduction highlight the use of the metal nanoparticle to enhance heat transfer and the changing in the modeling nanofluid. While single phase model assume uniform particle behavior, they often diverge from the experiment, making two phase model is a prominent alternative. The receive covering the variation study on the using the twisted tape insert to the boost performance and the identify a gap in the comparing single phase and a two phase simulation, especially regarding the number of twisted tape and the performance evaluation criteria. So, and here is the geometry of the twisted tape, and this is the one twisted tape and this is the two twisted tape, the model by using the simulation. This is the model and this is the governing equation and the numerical method. These are the empirical relation, and these are the equation standard capstone turbulence equations and boundary conditions, and the area the for the single phase flow and the two phase flow using the mass conservation, momentum conservation and the energy conservation equations. And after that, these are the graph we are plotting here. The x-axis represent the number of the y-axis represent the average Nusselt number. So as the number of the element increase, the Nusselt number decrease sharply at the first and then stabilize. This suggests that the refine the computational mesh initially affect the heat transfer result significantly. And yeah, the geometry boundary condition, numerical procedure, guide detail, and the validation. So here is the geometry. The tube has a radius of the 19 mm and the length 332 mm. One and two twisted tip are usually to analyze heat transfer enhancement, and the working fluid water copper oxide nanofluid with a nanoparticle volume fraction is a 0 to 4%, and the boundary condition where we are using here the boundary condition velocity inlet and the pressure outlet and the tube wall where the consider no slip condition with the constant heat flux. and the grade independency study. So, unstructured grade is used for the simulation, and which are showing in the figure 2. This is the figure 2, and after here, to in to ensure accuracy, grade independency in a check by the simulation flowing at the maximum Reynolds number. The Nusselt number remains stable beyond the certain number. Grade element configuration, grade independency, and the validation of the present results. So this graph consider of the three subplot ABC comparing the present computational result and the previous study. So here the graph number A, Nusselt number versus the Reynolds number. The current workflow the same trend as the Hamas configuration that the present model accurately predict heat transfer, and here the graph B and C. In the graph B, friction factor versus the Reynolds number, a decrease the trend observed the similar mass validating the friction factor prediction, and the C here the Nusselt number versus the Reynolds number, two phase single phase model. The two phase model giving the higher value than the single phase model suggests that the two phase approach better predict heat transfer in the nanofluid flow. Approach better predict that the heat transfer nanofluid. In a graph 5, Nusselt number versus the Reynolds number for the single and two twisted tape. So here as you see, the Reynolds number increase, Nusselt number also increase, indicating better heat transfer at the higher flow rate, and the curve for the two twisted tip lie above the other mean they provide higher heat transfer enhancement, and other also in other hand we see this reason emphasize this blue reason is emphasize that high Reynolds number above the 30,000, the performance difference between two phase and the single phase model become a more noticeable. The two phase model achieves significantly higher heat transfer rate than the single phase model. And in a figure 6, so in a figure 6 is the magnification of the figure 5, where it helps is a closely observe the difference between the single phase and two phase model under the different conditions, and the line in the graph represent different case based on the twist ratio and the flow model. In figure 7, if we see average Nusselt number versus the Reynolds number for one twisted tape transfer. As the number of the twisted tip increase, Nusselt number increase due to enhanced secondary flow and the turbulence, higher turbulence improving the convective heat transfer leading to better Nusselt number value. So here more twisted tip lead to higher Nusselt number and increase the observation in the fluid path generation, a strong vorticity improving heat transfer, and the effect of the twisted tip become more noticeable at the higher flow rate. This support idea that nanoparticle and the twisted tip together provide the best enhancement in the heat transfer. The friction factor for different nanoparticle concentration in the two-phase model, the results are compared with the smooth pipe theory-based prediction. So here at the lower Reynolds number, flow is more laminar, leading to the higher friction. As the Reynolds number increase, turbulent domain reduce relatively function. So more nanoparticle add resistance to the flow, increase the friction factor, and the twisted tip introduce swirling flow and the secondary turbulence, enhancing mixing. But then we see the figure number 10. This figure represents effect of the nanoparticle concentration phi on heat transfer for the different Reynolds number, each plot A and D corresponding to different nanoparticle volume fraction 1 to 4%. Two model as a compare single twisted tape and the copper nanoparticle water suspension to phase model. Here, the more the nanoparticle lead to higher thermal conductivity, improving heat transfer, and the turbulent increase heat transfer improve to better maximize result and discussion. So here figure number 9 and figure number 10. So this is here the Nusselt number versus nanoparticle volume fraction at the different Reynolds number. Two-phase model in a tube with a two twisted tape. Two-phase model in a tube with a one twisted tape. So figure number 9. This figure examining how the adding nanoparticle to the fluid enhance heat transfer for the different Reynolds number. Each curve represent specific Reynolds number 30,000, 80,000, 12,000, showing how Nusselt number increase at the nanoparticle volume fraction phi increase. And when we see here 2 seconds the flow direction velocity contour in the water flow. So figure number 23 is the Reynolds number is 3000 with a one twisted tape, and figure number 24 is the Reynolds number 36,000 with a two twisted tape. So here the figure number 23, this enhanced mixing the leading to the better than heat transfer, and the Reynolds number is 36,000. Figure number 24 is the higher the velocity gradient led to the strong turbulence, increasing the convective heat transfer. At the figure number 25, where the Reynolds number is the 3000. At the low Reynolds number, the swirling motion is not strong, which limit the heat transfer. And your figure number 25 and 26. So this figure depict the streamline and the velocity contour in the water flow different Reynolds number with a twisted tape. Figure number 25, where the Reynolds number is the 3002 twisted tape. So relatively weak secondary flow, low vorticity, swirling intensity, less effective mixing, and the heat transfer enhancement. Where the 20 figure number 26, Reynolds number is a 26,002 twisted tape, strong showing the strong secondary flow leading to better turbulence and the heat transfer, and the twisting tape induce high intensity vorticity, improving the convective heat effect, indicating the if higher Reynolds number result a stronger flow distribution, boosting the thermal performance. And here the figure number 27, here the figure number 27, 28, 29, and so this figure represents the temperature distribution in the symmetric plane for the different fluid condition. In the 27, temperature gradient is the visible but not highly pronounced, indicating moderate high heat transfer efficiency with the one twisted tape. And the 28 figure number nanoparticle enhance the heat transfer, resulting the more uniform temperature distribution, where the 29 figure at the higher the temperature distribution become the more uniform, indicating the improving the heat transfer. Conclusion. This study numerically investigates the heat transfer performance of the turbulent nanofluid flow in a tube with a 1 and 2 twisted tape using a single phase and a two-phase model. The result provides significantly insight into the impact of twisted tape and nanoparticle volume fraction, Reynolds number, in the heat transfer efficiency. Two-phase model provide a more reliable result than the single-phase model due to the ability to capture the interaction between the nanoparticle and the base fluid. Higher the Reynolds number improve the efficiency of, and the Reynolds number if 3000 Nusselt number is increased 95 times and the Reynolds number is 36,000, then the Nusselt number is increased 218 times in the tube with a two twisted tape, and the two twisted tape enhance heat transfer more than one. They also result at a higher pressure drop. Pressure and single phase model fail to accurately predict heat transfer in the presence of the twisted tape due to higher velocity gradient. Using twisted tape along in the water flow is a not optimal performance evaluation criteria is less than, indicating the poor balance between the heat transfer enhancement and the pressure drop. One twisted tape is a more energy efficient than the two. Performance evaluation criteria value is 2.184 for the one twisted tape and the 2.04 for the two twisted tape, making one twisted tape a better choice for the predicting the application. While the twisted tape nanofluid is significantly improve the heat transfer. They also increase the pressure drop, which must be considered in the system design. To two-phase model is best approach for the accurately predict the nanofluid behavior. Future research should explore the optimized twisted tape design and experimental validation due to enhancement efficiency.